Hello students, so this is the lecture for heart. Okay, so a few facts about the heart. It beats 100,000 times per day and a total of 35 million beats per year, and it pumps up to 3,600 gallons blood in a day. Alright, so functions of the heart. So the heart flows in a unidirectional way, meaning from the heart to the vessels, right? So basically the heart is two sides of pumps working side by side, working at the same time. One that is going to the lungs, meaning that is a pulmonary circulation, and then one that goes to the rest of the body, meaning systemic circulation. Okay, so we're gonna go more into detail on that later. So it creates blood pressure through contraction of the vessels and relaxation. Okay, so it connects blood vessels that transports blood between the heart and the other body tissues. So let me just erase this. There you go. As we know, arteries carry oxygenated blood and veins carry deoxygenated blood, right? So the arteries are going to carry blood away from the heart. Veins are going to carry blood towards the heart. Okay? All right, more detail into heart. So the heart has the shape of a cone, kind of like upside down, kind of this way. It's usually the size of a closed fist. So as we were talking during our respiratory system lecture, there's a space between the lungs where the heart is going to be located, and that is going to be called the mediastinum, right? And it's, as it says here, is the region between the lungs. Okay, it is a little bit rotated. 2/3 of a heart are going to be located on the left side. Okay, so as the lungs, there's going to be a base and there's going to be an apex. The difference here is that instead of the lungs, the base is going to be here and the apex is going to be inferior. Okay, just think about like an upside down cone. So again, base is going to be superior, apex is going to be inferior. Okay? All right, so here we have the heart with a little bit more of perspective. So we have here a right lung and a left lung. And this area contained between the lungs is called the mediastinum, right? Now we see it here. We got the rib cage where the lungs are going to be stored plus the heart, and here, if you guys are looking at, is the diaphragm, right? Lungs, and then heart is going to be contained here in this area called the mediastinum, right? Same thing here. We got anterior, posterior. All right, right lung, left lung. Okay, heart is being contained here, and this is vertebrae and other vessels. Okay, going back to the bigger picture here, as I mentioned before, as you guys can see, the heart is kind of like a cone laying down this way, right? So having that same concept, we're going to have a base on this side and the apex here. This is up, this is down, and here's we have our diaphragm, and below that is where we're going to have the GI tract, right? All right, so there is a membrane that surrounds, encloses, and also protects the heart. It's called the pericardium. And if you think about it, if we are explaining the words. In parts, you guys are going to see the peri means around, cardium, around the heart, right? It is also known as the pericardial sac, and it has different layers. So it has a fibrous pericardium, which is the outermost layer, and it's a fibrous layer, and it's dense connective tissue, all right? It prevents overstretching and overfilling of the heart. It also protects it, and also gives that anchoring to the surrounding structures, meaning the mediastinum, the lungs, so on and so forth. Below, or deeper, we have the serous pericardium, produces serous fluid known as the pericardium fluid, and this will make a little bit more sense once we see a picture of this, okay? This deep serous pericardium has two sublayers, a periatal layer and a visceral layer. We have seen this with the lungs as well as the peritoneum. So I hope at this point it makes sense what side is the visceral part and which part is the parietal part. Alright, so these sublayers, the periatal pericardium is the outermost layer, right? And is found directly deep the fibrous pericardium, okay? This one is the one that produces the serous fluid, okay? And then the visceral pericardium is the innermost layer, okay? It also produces serous fluid. This one adheres directly to the surface of the heart. And this one is also known as epicardium, above the heart, okay? Between these two layers, so we have a periatal pericardium and a visceral pericardium. We have this little space here, right? That is known as the pericardium space. It's a space between these two layers, and this is where that serous fluid goes. And what it's doing is just lubrication, because these two fibers are gonna be rubbing against each other, and we want it to be smooth, right? As it says here, lubricates and decreases friction as the heart is pumping. All right, so here's where things make a little bit more sense, okay? So here we have, and I'm gonna use colors for this one, a fibrous pericardium. You guys can see it here. It's this fibrous layer here. And then this layer here is going to be the serous pericardium, okay? So in this area, and I'm gonna use another color, it's going to be the periatal pericardium. This area down here is the visceral layer of the pericardium, okay? I'm gonna erase some of this. Between these two layers, we have the pericardial space or cavity, and this is where the fluid is gonna be present, so the friction is lessened. Another layers that we're going to see here is the epicardium, which is the same one as the visceral layer of the pericardium. Then we're going to have a myocardium, which is the middle layer, and then an endocardium, which is the innermost layer, and then the heart chamber, okay? This makes also a little bit more sense. So if you guys think about the pericardial cavity, it's just like a balloon, and then we put a heart in it. And as you guys see, this pericardial sac is just surrounding the heart, okay? So we have a serous pericardium here, the outermost layer, sorry, let me just redo this for you guys. So the outermost layer, meaning this area here, is going to be the periatal pericardium, right? The visceral pericardium is going to be the one surrounding this body here, the heart, right? And this space here is the pericardial cavity, and that gives a little bit more perspective. So the pericardium or pericardial sac is that area that is going to engulf the heart. And it looks like this, okay? Now we're going to talk about the layers of the heart proper. We have an epicardium, myocardium, and endocardium. Let's break down the words a little bit. Epi means above the heart. Myo means the muscle area of the heart. Endocardium means the internal area of the heart. Okay? Perfect. So the first layer, the epicardium, it's a thin outer layer, and it's a serous membrane because it's the same layer as the visceral serous pericardium. You remember that innermost layer? It's the same one. It's one and the same. Okay? It's made of simple squamous epithelium, and it has underneath adipose tissue, meaning fat. The fatter we get, the thicker that area is. Then we have the myocardium, is the middle muscular layer. This one is responsible for the contraction of the heart. It's a tissue that is arranged in circle bundles like this, like an 8. And it's made up of mostly cardiac cells. So we talked about smooth muscle, skeletal muscle, and then we have cardiac muscle that we know is specific to the heart. There's also being crisscrossed by collagen and elastic fibers. And this fiber is made up the cardiac skeleton that doesn't have any function other than structural and is where the heart is anchored to. Okay? And also provides support. This part over here, it says it's not electrically excitable because this is just structure, okay? And we're talking about these fibers, okay? The muscle itself, it's excitable. The structure is not. And these are called cardiac muscle fibers, surrounding the atria, surrounding the ventricle, okay? The endocardium is the innermost layer. It's lining the inside of the heart and it's made of simple squamous epithelium. At this point, you guys should know what squamous epithelium looks like. And then above, I should say, because we're looking from like inside this tissue, there is connective tissue, which is just a little bit of like, think about the lamina propria of another tissues, okay? Now putting everything together, let's look at it from the outside to inside. So the first area we're gonna have here is epicardium, okay? And here's when we see those simple squamous epithelium. Underneath is the areolar tissue, which is fat. And then we have myocardium, right? And as you guys can see, there is cardiac muscle here, all right? And then underneath this guy, we have endocardium. You can see here the squamous epithelium. And underneath, there's a little bit of connective tissue, okay? Let's break this down and make sure you guys comprehend that. Talking about the heart proper, we have epicardium, myocardium, endocardium, okay? Outermost, middle, innermost. Now putting everything together, so we have a fibrous pericardium. We have that layer called as the serous pericardium. We have a parietal pericardium, a visceral pericardium, and then we have the pericardial cavity. Then we have one and the same. The epicardium is also the visceral pericardium. And then underneath, we're going to have some fat or areola tissue. And then underneath that, we're going to have the middle section, which is called the myocardium, right? And then we're going to have the innermost layer, which is the endocardium. Below that is the heart chamber. This is where blood is just going to be stored and then pumped. Okay? Okay, so the fibrous cardiac skeleton of the heart. This is what we were talking is what makes the structure of the heart, okay? Connective tissue, collagen, fibers, and elastic fibers. It provides a framework, meaning the infrastructure of the heart. It also provides insulation between the atria, which is the two chambers, and the ventricles, okay? This prevents all four chambers from contracting at the same time, meaning that if we have a right atria, a left atria, a left ventricle, and a right ventricle, this guys needs to pump first, and then this guys need to pump first because blood is going to come this way and then shoot out. If all these guys are pumping at the same time, nothing is going to come in, nothing is going to come out, so it's useless. That's one of the functions of the fibrous skeleton of the heart, okay? Think about this fibrous area as insulation and not electrically conductive. What is electrically conductive are the cardiac skeleton muscle, okay? This is another look, and then we're gonna introduce new structures. Okay, so we have myocardium, and we already talked this one is the middle area. But then we're going to have valves. So we have a division of chambers. Think about the heart as a 4 chambers area. We have, again, right atrium, right ventricle, and left ventricle, okay? So between those guys are going to be connections or doors. We have a valve here, and then we have another valve here, okay? There are other 2 extra valves, but I'm going to introduce those later, okay? So these guys here are the valves between the chambers. These guys here, okay? Let's start with the left one. The left one is called mitral or left atrioventricular valve. Does that make sense? Because it's going from the atria to the ventricles, right? Atrioventricular valve. And this one is the left one, aka mitral, because it resembles a mitre, something that the Pope has. The thing you have to remember from this one is, of course, where it's located, the name mitral, but also has 2 valves, okay? And this will make sense later, because then we have a tricuspid valve. This one is the right atrioventricular valve because it has 3 pieces. Tricuspid. The way I remember this is right, left, 2. Okay? Mitral is left, tricuspid is right. Okay? So, when blood goes from the atria to the ventricles, they have to go somewhere else, right? And this is where 2 extra structures come into place. We have an aortic valve and a pulmonary valve. Going back to our 8 example of what's systemic and what's pulmonary, this will make sense, okay? We have a pulmonary valve that is going to go to the pulmonary circulation from the, where is my friend, the right side. So this guy basically is going to be present in this area where blood is going to come from the right atrium, right ventricle, and then to the pulmonary valve, all the way to the lungs, right? Now, it will be a similar case for a friend, the aortic valve. and it's kind of like a giveaway also very common. These guys always have three valves, as you guys can see. The aortic valve goes to the aorta, and this is where it plays to the systemic circulation. So blood is coming from the lungs to the left ventricle, to the left atrium to the left ventricle, and this is where our friend, the aortic valve, is going to be present to go from the left ventricle to the aorta, right? And then to the body. Okay? And you guys see it here. Tricuspid, mitral, aortic valve, pulmonary valve. Okay? Now we're going to go to the cardiac muscle cell structures. So, as we were talking, we have smooth muscle, skeletal muscle, and then we have cardiac muscle. Skeletal muscle and cardiac muscle are very similar, but they have several differences. Okay? Starting with, they only have one central located nuclei with a lot of mitochondria. If you guys remember your biology, the mitochondria in the cells is the powerhouse of the cells, okay? This is where all the energy is produced. The muscle fibers are short, thick, branched, and striated, and you guys will see. Whenever I think about the muscle cells of the heart, I think about pants because they kind of look like that. They kind of look like little pants with stripes, with a nuclei and tons of mitochondria, okay? These muscles are self-excitable, meaning that they don't need any stimuli from me to pump. And if you think about it, you don't have to think about pumping your heart all the time, right? They also have the structures called the intercalated disc. And this is basically, if you guys think about a hallway, and you have different rooms, meaning different cells, the intercalated disc are these walls, but these guys also divide but also connect between the cells. The reason is that this self-excitable portion needs to be efficient, and these junctions allow that because they have gap junctions, meaning that the electricity and the stimuli is going to go through this instead of doing this. If you guys think about it, I don't have to go be knocking doors. Instead, I can go through the walls. Okay? This is called a functional syncytium because it behaves as one single coordinated unit instead of different units, because we need our heart to be as effective as is functionally possible. Okay? The other piece that you guys see here is the desmosome. Think about desmosome as a structure that is going to be like pins or like a zip tie. So you have a structure, a wall, two pieces of cells on each side, and basically the desmosome is like those pieces that is going to attach, kind of like buttons attaching two things together. Okay? You will see this in a lot of cellular structures, but these are very evident in the intercalated disc. This is something that makes more example. So we're looking here, a picture of cardiac muscle. You guys see the cells nuclei here. And also you see in the striated look of this muscle cells. But if you guys look closely, there's like something like a line that is going like vertically. These are the intercalated disc. If you separate a single cell, kind of branches out, but kind of looks like pants. That's what I think about. It looks like pants. Okay? And if I want to communicate information, meaning like a stimuli, like contraction, let's say, instead of going from cell to cell, they're going through because it's more efficient. This is what it says here. The intercalated discs are connected so the function goes through. Okay? This is only present in the cardiac muscle because of the nature of what is needed to be done or what's expected to be done from the heart. Okay, so here we're seeing the differences between skeletal muscle and cardiac muscle. As we were talking, they're similar, but they're not the same. So they are both striated. And that's what you'll hear called striated muscle. It's long and it's cylindrical, but this one is short and branched. As we were talking, it looks like pants. They kind of branch that. The muscle cells, meaning the skeletal muscle cells, they have multiple nuclei. Cardiac muscle doesn't. And as I said before, they don't have gap junctions because the function of the heart has to be efficient. Skeletal muscle doesn't have to be. It contracts as a unit? It doesn't, because we need muscles to move independently, because if we all contract at the same time, we will be just constantly cramping. The heart not, because it needs to have a specific effective contraction pattern, right? The tubules are abundant and it's just like junction, it has a contraction function. The things that you guys need to know for this matter is that the cardiac muscle doesn't have them or has fewer and they're wider, okay? Sarcoplasmic reticulum, it is a structure that is in all muscles and is where some ions are stored. In the sarcoplasmic reticulum, it's a lever and it has terminal cisterns, and this is specific to the contraction of the skeletal muscle. In the cardiac muscle, you need it because it's not the function that is expected in this area, okay? This one is the sarcoplasmic reticulum. This is where calcium is stored, is needed for contraction. You need calcium for both, but the function is going to be different in the heart, okay? That's why that's structural difference. The calcium is going to bind to troponin, yes, in both, okay? Pacemaker, of course, you don't need a pacemaker in your skeletal muscle. You don't need a pacemaker in your leg, but you need it in your heart, and we'll talk more about it later, okay? Tetanus possible? Yes, a contraction can happen. Doesn't happen on your heart. It's not affected by it. All right. Then the last one is supply of ATP. You guys remember the ATP is kind of like the currency for energy. That's why we need a lot of sugar, because sugar is one of the fastest way to get ATP. And ATP is the molecule of energy that is needed for activity, meaning any activity, either to produce or metabolize that, but also to procreate and do the movement piece of contraction. With your skeletal muscle, you can do it in an aerobic way or anaerobic way. Cardiac muscle needs only aerobic. That's why it's important to supply to the heart. One of the structures that consumes most energy from our bodies are heart and also the brain, okay? And that's why they're also so sensitive to the lack of oxygen. That's why when you have a stroke, it's very bad. Same thing goes for the heart. If you have an infarct or myocardial infarction, that's why it is so fundamental to it. Okay, so this is like a diagram, and we're gonna see the desmosome. See, it's like a little bit of zip ties are just connecting two walls together, right? The gap junctions, they're just like doors where ions are gonna go through. And here we see nucleus, but also we see the intercalated disc. So if you guys think about it, this is one cell, this is one cell, and this is one cell. Of course, we don't see nuclei here, but we expect to see nuclear. This is just like the way it was just cut in the sample, okay? This is more like a diagram. If you guys think about it, this is a whole cell. You got the nucleus here, and if we open this, you guys see all the mitochondria that's going on. Okay, extranuclear here. But also you guys see the intercalated disc here. And this is where it's showing like the gap junctions or also the desmosomes. You see the mitochondria here, and also you see the tubular. This is where some ions are gonna go in and be distributed. This is the sarcoplasmic reticulum. This is where some ions are gonna go. And then this is just like a more in-depth structure. I don't expect you guys to know this because you guys saw this at some point last semester. What I want you to know is how to identify the cell and the basic structures known as the nuclei, the intercalated disc, know that there are junctions there and what they do, and the desmosomes, okay? And also that it has multiple mitochondria. That's as minimum as I expect you guys to know. All right, so now we're gonna talk about more anatomy of the heart. So as I have said, the heart is surrounded by fat. All right, and if we gain weight, that fat tissue is going to increase. But also outside of the heart, there are going to be grooves called sulci, and they're important because they kind of demarcate some structures. What differentiates the atria from the ventricles, but also is where some vessels are going to be contained. Not only the heart needs to have blood that's going to pump through, but also it's going to need blood to pump and work itself. As I said, the heart is greedy and it needs a lot of blood and oxygen. All right, so let's talk about the coronary sulcus. So those are external boundaries that demarcate the atria and the two ventricles, okay? So the first one that we're going to see here is the coronary sulcus. And there it is, where the right coronary artery is. And it is, and let me use another color, this area here, okay? Then we have another coronary sulcus that is going to be here, and this is where the left coronary artery is, okay? There is another sulci, or there is another sulcus I should say, and this one is here, okay? That one is where the great cardiac vein is, but also the anterior interventricular artery is. So let's remember our chambers again and use another color. So I have right ventricle, left ventricle, right atrium, left atrium, okay? So we have one of the sulcus that divides these two, another sulcus that divides this atrium from this ventricle, but then we have an interventricular sulcus between these two because there are two ventricles here, right? A little bit of review. We have the base of the heart and the apex of the heart, okay? Left side, right side, okay? Let's just erase some of this stuff so we get more familiar with, okay? So as I said, these are external boundaries that divide atria from ventricles and in between ventricles. We have this sulci here where the anterior interventricular artery is, but also the great cardiac vein, okay? We have this sulcus here that's going to divide right atrium from left ventricle. And this is where the right coronary artery goes through. On the left side, we have a left sulcus, and this is where the left coronary artery is, okay? All right, so we talked about a little bit of the anterior interventricular sulcus. It's the one that divides the two ventricles, the right ventricle and the left ventricle. And this is where the great cardiac vein is, but also the anterior interventricular artery, okay? Dividing these two, from left to right, okay? then this is from behind, meaning posterior, right? And we are going to see the division here is the posterior interventricular sulcus. So it's in between the ventricles and it's posterior, meaning the back, right? So this is the heart from the back. If you guys see, we have right atrium, left atrium, we have a left ventricle and a right ventricle, okay? The sulcus is going to be here, okay? If you guys look to the text, it says posterior interventricular artery, which is the interventricular sulcus, okay? The things you need to remember from this is, one, that those sulci are kind of landmarks that divide some areas, okay? So we have a right sulci that is going to divide the right atrium from the right ventricle, right? And where the right coronary artery is. A left sulcus where the left coronary artery is, that is dividing the left atrium. I repeat that, left atrium from left ventricle, okay? And then on the front, meaning anterior, there's that interventricular anterior sulcus, where the interventricular artery is, right? Now in the back, we have a posterior interventricular sulcus, and it's the one that we're seeing on this slide. That is divided into two ventricles because it's interventricular, right? And this is where also the posterior interventricular artery is, okay? Perfect. So now we have been talking about like atrium and ventricle and so on. So now we're gonna go a little bit more into depth. So think about the heart as 4 chambers, right? So we have a right atrium and a right ventricle, then a left atrium and a left ventricle, okay? If you guys think about a building, a lot of buildings have an atrium, right? And that's why these guys are called atrium. So we have right atrium, left atrium. Below these guys, they're gonna be the ventricles. So we have a left ventricle and a right ventricle, right? So in between these guys, they're gonna be valves because the blood has to flow from the atria to the ventricles, right? So we have a left atrioventricular valve and a right atrioventricular valve. A tricuspid valve because it has 3 pieces, and a mitral or bicuspid because it has 2, right? Right, so now we're gonna talk about chamber per chamber, okay? So right now we're gonna talk about the right atrium, which is this guy located here, okay? So it is the chamber that is in the right superior portion of the heart. It is thin-walled, and it's going to receive deoxygenated blood from the body through 3 main structures: a superior vena cava, an inferior vena cava, and a coronary sinus. So this is the right atrium. We're going to receive blood from the superior vena cava, bringing all the deoxygenated blood from the upper extremities, and then an inferior vena cava that is going to bring deoxygenated blood from the lower portion of our body, okay? Then we're going to have the coronary sinus, and I'm going to use another color so this makes a little bit more sense. This coronary sinus is behind the heart, and it's also going to pull all the oxygen, the deoxygenated blood that is coming from the heart itself, okay? There are some structures called the pectinate muscles, and they're going to be found in the lining of the walls, meaning the interior chambers, and they're going to look like this, okay? There's also right, or we call it muscular and patch shaped, okay, and it's called an atrium because it resembles that shape, okay. As we were mentioned, okay, so let's take a few looks to the exterior structures of the heart, okay. So we have the base of the heart here, then we have the apex. Those are already established. I just wanted to go over those guys again. And now let's look at the sulci. So we have an interventricular sulci that is going to be here. Let's use a different color. So you guys will see the interventricular sulci here. And on the right side, you guys are going to see that it's the right ventricle and the left ventricle. And this sulcus, you guys are going to have the great cardiac vein, but also the anterior interventricular artery, right? Then on the right side, there's the right sulcus, and there is the right coronary artery. It's dividing the right atrium from the right ventricle. Same case on the left side, we have a left atrium and a left ventricle. Okay? Now let's get familiarized with other structures here. We are going to see on your right side two big veins. They are coming from the body, one in the upper portion. Right, from the previous slide we were talking about these two big vessels here. They are the superior vena cava and the inferior vena cava. Okay, so these guys are coming from the body to the heart. The superior is the upper extremities, the inferior is the lower extremities. They have venous blood, meaning low in oxygen, and they're going to come to this little chamber here known as the right atrium. Here we're going to see as well a few other structures. Here we're going to see the pectinate muscles in the wall of the right ventricle. We also have a tricuspid valve, and we know it's tricuspid because it has three, right? So tricuspid right. Our friend below the ventricle is going, let me repeat that. The guy below the atrium is going to be the ventricle, right? This is the right ventricle. These friends over here are the pulmonary valves. They look like swallow nests. They also are called semi-lunar valves because they kind of resemble a crescent moon if you think about it. There are three. So if low oxygen blood is coming to this atrium and then going to this ventricle and then going to a vessel called the pulmonary artery, it means these guys are going to go where? The lungs, right? This is when it's a little bit confusing because we've been talking about that arteries carry oxygenated, rich blood, and veins do the opposite, right? This is a little bit confusing because only in the heart you will see that the pulmonary artery carries low oxygenated blood, but the pulmonary veins carry oxygenated blood. The reason because of this is just because of the structures of how these veins were formed. The things that you need to know, if it's on the right side, is low in oxygen because the blood is coming from the body to the lungs, from the lungs to the left atrium, from the left atrium to the left ventricle, and from there to the rest of the body. And this is when we are talking about the 8-shape circulation, meaning pulmonary circulation and systemic circulation. So this portion here will be part of the pulmonary circulation. This portion over here will be part of the systemic circulation, okay? So now this is a posterior, meaning from behind. Look at the heart, and we are going to see some structures that we already talked about. So we have a sulcus here. There's the coronary sulcus dividing atria from ventricles, right? This side is the right one because we're seeing it from behind. This one is the left one. On that on that sulcus, we're going to find the coronary sinus, which is a structure which is basically a vein, which is going to collect the low oxygenated or deoxygenated blood. Okay? Going perpendicular or vertical, we are going to see the posterior, because it's from behind, interventricular sulcus. Okay? And there's going to be a posterior interventricular artery and a middle cardiac vein. Okay, this is from behind. Okay, guys? We have a left ventricle and a right ventricle. Let's erase these things a little bit. And now let's see what structures we see here as well. So here you guys are looking at the entrance of the inferior vena cava that is coming from the lower extremities and bringing all that deoxygenated blood to the right atrium, right? Same thing with the superior vena cava. Deoxygenated blood that is coming from the upper extremities to the right atrium, okay? Another structures to get familiar with are here as well, and this is a perfect side to see 2 and 2 with a total of 4 structures called the left pulmonary veins. These guys are coming from the lungs to the heart, bringing oxygenated blood. As I said in the previous slide, this is when it gets confusing, and this is the only exception in this case. The pulmonary veins in the heart are bringing oxygenated blood. The pulmonary arteries are bringing deoxygenated blood from the heart to the lungs, okay? These guys over here, these 4 pulmonary veins, are going to the left atrium, okay? I just wanted to mention that because this is a perfect portion to talk about them because you can see them in more detail and perspective. Here we have the aorta, and I think a lot of you guys are familiar at least with the name, the aorta. So this guy is going to come from the heart and descend to the body, and also has some branching so it can go to the upper extremities, okay? And that's pretty much it. A little bit of review. Apex of the heart, base of the heart. Okay, so this is another view. This is from the front, meaning anterior, and here we can see a little bit more structure. So we have a right atrium, a left ventricle. We also see the ascending aorta and the descending aorta, okay? We also see our friend here, the superior vena cava, and you guys will see sometimes this one be just like simplified as SVC for superior vena cava, and then IVC for inferior vena cava. So bringing the oxygenated blood from the upper extremities when it's the superior vena cava, and the oxygenated blood from the lower extremities when it's the inferior vena cava. All right, so this, let me use a different color. This chamber, as we said, is the right atrium, right? So blood is going to flow by passive flow, but also when this guy contracts to the right ventricle, right? And then, if you guys notice this myocardium, which is the middle layer of the heart, is supramuscular. The force needed in this portion of the heart is greater than what we need in this portion, okay? And if you guys notice, the left portion is more muscular because the force against it is higher. Why? Because the left side is going to be pumping to the systemic system, while this guy here just has to work against the resistance that is present in the lungs. Pulmonary circulation, systemic circulation. Okay? So going back to the right ventricle, you guys see here the tricuspid valve, because he has 3. Okay? This area here is the right ventricle. Again, the muscle layers, meaning the myocardium. And then we see the semilunar or pulmonary valves. There are 3. The reason that they're kind of like a cup is because when blood backflows, they close. Okay? This is kind of like a safe skip. So there's not enough backflow blood that goes here, and then there's no purpose of pumping blood somewhere if it's back in back, right? So from here, we're going to go to the left lung. And from here to the right lung. And this is where the gas exchange is going to happen, right? Also, if you guys have noticed here, there's like a little ligament. We talked about a ligament in the liver, that it's a remnant of the umbilical cord. Well, this guy here is a remnant from something that is called fetal circulation. When we are inside mom, we don't need a lot of this circulation to happen here. So there is a connection here called the ductus arteriosum when you are a baby inside the mom, and this is when mixing of the blood is going to happen. Once we are born, that ductus is supposed to close because we don't want the mixing of oxygenated blood with deoxygenated blood, right? So this needs to be closed, and with time it becomes a ligament. Sometimes with babies have some defects, we want that open, and we give some medications to keep these guys open. One of the medications that we give is ibuprofen, believe it or not, because it reduces some substances that promote the closing of this. So if this is patent, there's mixing of blood, and in those cases, we want that for those kids. In a healthy human being, you don't want that open after they're born, okay? Because we want these guys to be parallel, but never mixing. Okay? All right, so the interatrial septum. Let's divide words again. So septum is a dividing from something, right? It's a wall. Think about a wall. It's a septum is a wall. We saw a septum of the nose. This is a septum in the heart. So this one is inter, so it's in between something. Atrial, so it's between the atria. So it's a septum that is between the atria. As it says here, divides the right from the left. It's a partition. And we were talking before about that ligament. This is another piece present when we are in utero, meaning inside mom. It's called the fossa ovalis, and basically it's a hole that promotes mixing of blood, because that's something what we want while we are inside mom. Once we are born, we don't want mixing of blood because it's not effective, and that becomes the foramen ovalis. We don't want that open, okay? So from foramen ovalis, the fossa ovalis, it's just like a remnant of that, okay? And you see it here. So the fossa ovalis is the remnant of that fetal structure, okay? This usually closes itself. 25% of human beings walking around this earth sometimes have it. And this little, just like mixing of blood, I call it like a little fart of blood because it sounds like a little extra sound. It's okay, and sometimes it closes, but sometimes in some people it stays open, and there's an increased risk for clots that can cause a stroke. Okay? Here is the same structure. We already talked about the atria, a right and a left one, ventricles, right and a left one. We have the semilunar or the pulmonary valves, And there's some, and you guys don't see it here, but it looks like a little butt if you guys look about it here. Those are the aortic valves. There are also three. And these guys are the valves in between the left ventricle and the aorta. Okay? So also talking about atria and ventricles, we are going to see this valve known as the bicuspid valve, but also it's called the mitral. Okay, so you'll see this two used interchangeably. Okay, so also here we are going to see, and I'm going to erase this here. All right, is where the fossa ovalis is. So tucked behind this two structures here, you guys will see the interatrial septum. So this division is here between the right atrium and the left atrium. This fossa ovalis is just like a little membrane that is going to close or eventually close once we are born. Okay, so the mixing of the blood doesn't happen because we don't need that anymore. The other ligament that I was telling you guys about is here, and it's not present here in this diagram, but it's the ligamentum arteriosus. Okay, apex, base, valves, interventricular valves, right one and left one, pulmonary valve, aortic valve. Okay, and then we're going to talk about another septum in between the ventricles, and guess what it's called? Interventricular septum. All right, so right ventricle, as I said, is thick walled, located at the right piece of the heart, inferiorly, and the blood is going to come from the atrium, the right atrium, through the atrioventricular valve to the right ventricle, and all this blood, since it's coming from the body to the heart, is going to be deoxygenated. Okay, keep that in mind, deoxygenated. All right, so there are trabecular carinae fibers, chordae tendineae, and the papillary muscles. You guys will see that in some diagrams, so don't get too confused. Okay, so from the right ventricle, the blood is going to pass to those pulmonary valves, the ones that I was telling you guys about that look like little crescent moons or like little swallow nests, and from there through the pulmonary arteries is going to go to the lungs. Okay, so the gas exchange happens. Okay, prior to become the pulmonary arteries, it's something called the pulmonary trunk. Okay, and then the pulmonary arteries. It's just like some branching of the branching. So we have a pulmonary trunk. Let me just erase this a bit. And basically what it is just some branching. So we have a pulmonary trunk that is going to branch in two, and those are going to be the pulmonary arteries. You're going to have a left pulmonary artery and a right pulmonary artery that are going to be stemming from the pulmonary trunk. Okay, here we see it. So this is another diagram of the heart, but we're going to talk about the structures that we just talked about. Okay, so we have a chordae tendineae, and basically these guys are going to attach the tricuspid valve to the walls of the heart, to the walling of the heart. We also have the trabecular carinae, and they're just like little holes, kind of like they look like little caverns. Okay, and then these little guys here that look like papillae are going to be called the pectinate muscles. We saw some of the structures in the right atrium here. Okay, speaking of the pulmonary trunk and the pulmonary arteries, we're going to talk about them next. So blood is flowing from the right atrium, passing through the tricuspid valve to the right ventricle, and then the squishing or contraction, also known as systole, of this chamber is going to push blood through the pulmonary valves to the pulmonary trunk, and from there it's going to go to the left pulmonary artery to the left lung, and also at the same time to the right pulmonary artery going to the right lung. Okay, as I said before, so we have a wall also dividing these two. So we have a inter, meaning in between, ventricular, so in between the ventricles, septum, meaning a wall. So it's a wall between the ventricles, right? That's what it is. Some babies are also born with some defects where that septum is not fully closed, so there's mixing of blood. And as I said, we don't want that in a living human being. Again, so interventricular septum, so we have it here, right? And of course, as I said, we don't want mixing of these two because we have oxygen-rich blood on this side, oxygen or deoxygenated blood on this side, right? So stick this in your mind. If it's on the left side, it's going to be oxygen-rich, okay, because it's coming from the lungs. If it's in the right side of the heart, it's deoxygenated blood because it's coming from the system to the heart. All right, so now let's talk about the left atrium. So again, it's thin wall because we don't need the amount of force in that chamber, and the blood that is going to be coming to this one is going to be from the lungs to the heart, meaning that it's going to be rich in oxygen, meaning oxygenated blood, right? There are 4 pulmonary veins, and those are the ones that I showed you guys when we were looking at the posterior view of the heart, okay? So these guys also have in their lining the pectinate muscles, and those are the ones that look like a little papillae, and that's why they're called that way, okay? We saw them on the other 2 chambers that we already talked about, okay? So on the left side, we don't have a tricuspid, but a bicuspid valve, okay? And it's also known as the mitral valve because it resembles a mitre, and this is a piece of adornment that the Pope wears. So just a little factoid, okay? And from there, the blood goes to the left ventricle, okay? Again, left side, oxygenated rich blood, and in there are 4 pulmonary veins, okay? So from the left ventricle, oxygenated blood is going to go through the bicuspid valve to the left ventricle, and then it's going to be pass through the valves known as the aortic valves to the aortic trunk, and then to the rest of the body. And here we see just a little bit of it. We're going to see a little bit more into detail from the inside. So we have a left atrium here, and then a left ventricle, okay? We also see here the pulmonary trunk here, but also we're going to see the ascending aorta, which means the aorta is going up and then to the rest of the body, okay? Here we see a little bit more into detail. So we have the pulmonary veins, and that's what I wanted to show you guys, the pulmonary veins posteriorly, because you only can see 2 here because the other ones are covered by these guys here. So there are 4 coming from the lungs, of course 2 from the left, 2 from the right. Then as you guys see, it's just thin compared to this guy here, okay? Both sides, it's a same layer known as the myocardium, right? All this is myocardium. But also has a little bit of pectinate muscles here, like you guys saw here, and like you guys saw here, okay? Same structure, just different place. In between the atrium and the ventricle, we're going to have a atrioventricular valve, known as the mitral valve or bicuspid valve, because it has two, in contrast to this guy here that has three, and that's why it's called tricuspid. Okay, so we have oxygen-rich blood, meaning oxygenated blood, coming from the lungs through here, and of course the same one from the right side, and then squish by contraction and passive filling to the left ventricle. Then the contraction of it is going to push the blood to and through the aortic valves to the ascending aorta, and then through the rest of the body, meaning that this piece here is part of the systemic circulation, and the resistance is greater there, and that's why you guys see that this ventricle here is thicker than the rest. Okay, now we're going to talk about the left ventricle. As I said, thick wall chamber. Okay, is the thickest and the largest, and we already talked why, because the resistance that is going to be found in that chamber is going to be greater because it's pushing against the systemic resistance. Okay, so we have already talked about this structure. So the trabecular cornea is those little caverns in the chamber wall, the chordae tendineae, which are attaching the valve to the walls, and also the papillary muscles. Those are the ones that we already talked about in the other structures of the heart. Again, if it's coming from the lungs, it has to be oxygenated because the gas exchange already happened, right? So from the left ventricle, the blood is going to travel through the aortic valve to where? Passing through the aorta to the rest of the body, okay? This is where the systemic circulation happens. So we talk about the right side being the pulmonary circulation. This guy is the piece of the systemic circulation. Greater resistance because we're talking about a greater body, our body itself. So that's why it has to be stronger. All right. We are very familiar right now with this piece of anatomy. So we are talking about the left ventricle. And as you guys see, compared to the rest, this wall here is thicker. When people are starting to get hypertension, this piece here has to work harder and harder and harder and harder, and it gets sometimes very thick. And that is part of the left ventricular hypertrophy. When it's super thick, it's not as effective, and this is when we run into problems. Oh, now we're going to talk about the myocardial thickness. So as I said, like this myocardium is in the 4 chambers, and that's going to help with the amount of force, okay? As we were saying, the left ventricle pumps throughout the entire body, and that's why it's the thickest, okay? The right ventricle is thicker too, but it's less thick because it has a lesser resistance to work against too, okay? And that's why. So if the resistance is lower and also the distance is lower, that's why this right ventricle is going to be smaller, because it doesn't have to work as hard. Here's a little diagram, and that's what we're looking at too. See how thick this guy is here, and how not that thick this guy is here. Both of these guys are thicker than this guy's here because they don't have to work as hard, okay? This guy, meaning the left ventricle, has to work harder because the distance and the resistance is greater in the systemic circulation than the pulmonary circulation. All right, the heart valves. So we already have mentioned and talked about them. We have atrioventricular valves. You will see them as well as the AV valves. And we know that there is a tricuspid from the right side and a bicuspid from the left side. So we know this one is right. AV, meaning right atrioventricular valve. And we have a left bicuspid atrioventricular valve, also known as the mitral valve. Okay, dividing the atrium from the ventricle, and they're located in between. Okay, on top of those, we have the aortic and pulmonary valves. So this guy is here, is from the left. This guy here is from the right, because they're going to different places, right? The pulmonary on the right is going to go to where? The lungs, right? The aortic is going to go to the aorta and the rest of the system. They are also called semilunar because they have like the shape of a crescent moon, like this, but just like, upside down. They also remind me of like a swallow's nest because they're like kind of like a little cup like this, and they're three, okay? Meaning three valves on each side. So three on the aortic, three in the pulmonary, okay? And this is like the little border or valve that is going to be from the ventricles to its respective vessel, meaning either the pulmonary or the aortic. So when the ventricle contracts or the systole happens, the pressure is going to push and open these guys, but when the blood wants to back up, they close, and that's why they have this shape. If you think about it, they're like three little cups that when they filled up, they close. And we see them here. So think about it, like blood goes here from the atrium to the ventricle, and then when the ventricle contracts, whoosh, it just push. If the blood tries to backflow, these valves close, and that's why there's no backflow of blood. And the same case happens here. The closing of this one, which is the tricuspid valve, and the closing of this left bicuspid valve are the cause of the first sound of the heart, the lub that we call. The closing of these two here causes the other sound of the heart. So the lub, dub, the doo is that are caused by the closing of these valves. So when you hear the first lub, meaning the doo, that is the closing of the atrioventricular valves. The dub, boom, is the closing of those valves in the aortic and pulmonary valves. Okay? At this point, we're very familiar with a lot of the structures. Atrium, right, left, ventricles, right, left, valves, both aortic and pulmonary, atrioventricular ones. Which one is the left ventricle? Which one is the right ventricle? The vessels, the aorta and the pulmonary vein. Sorry, the pulmonary artery, and then the pulmonary veins on each side, right? So low oxygen blood is coming on the right side, and oxygen-rich blood is coming on the left side, right? And this is when we are talking about the pulmonary versus the systemic circulation. So let's use a different color for this. Let's do blue. Okay, so coming from the lungs is going to be oxygen-rich, meaning oxygenated blood that is going to come from the gas exchange and the pulmonary capillaries, and is going to be sent to the right atrium, right? The left atrium, okay? From there, it's going to be pushed through the bicuspid valve to the left ventricle, right? After being contracted, it's going to go through the aortic valve to the ascending aorta and the systemic circulation through all the arteries. And then capillaries, gas exchange, meaning the internal respiration happens here, meaning the gases that the cells are given to the red cells. We talked about this in the internal respiration, going through the coronary sinus, which is in the heart, the inferior vena cava, which is all the deoxygenated blood coming from the lower extremities, and from the superior vena cava, meaning all the upper extremities. Then they all pour into the right atrium. And then from the right atrium is going to be pushed through the tricuspid valve to the right ventricle. Then the right ventricle is going to contract, meaning systole, and take it to the pulmonary trunk, and then to the left and right pulmonary arteries, going to the lungs, where this deoxygenated blood is going to have a gas exchange, and the cycle repeats. Okay? And this is what it's telling us here. Okay? And this is the part of the 8 kind of structure it's telling us. So think about like this. Okay? Pulmonary, systemic circulation. A little bit more into detail. So this is just a little bit like backwards. So let's start from here. This will be our starting point. So we are getting oxygenated breech blood, meaning oxygenated blood, to the right atrium. The right atrium, it goes to the right ventricle. So we're here. Blood gets pushed through the ascending aorta, and then it goes everywhere in the system, systemic. Okay? Here, where all the internal respiration process happens and the waste is collected, is going to lose the amount of oxygen, right? And this is where in the capillaries is happening, and it will become deoxygenated blood that eventually, through the structures we already talked about, meaning the IVC, inferior vena cava, superior vena cava, and the coronary sinus that is around the heart, it's going to come to the right atrium, and then right ventricle, push through the semilunar or pulmonary valves to the pulmonary trunk over here, then go to the left and right pulmonary veins to the lungs, where the gas exchange happens, and it repeats this cycle again. Pulmonary circulation, systemic circulation. Okay? So the heart itself needs blood, needs oxygen because it's doing a lot of stuff. 25% of our energy, oxygen, and glucose is being used by our heart. There's another greedy organ in our bodies that is going to be the same, is going to be the brain. But if you think about both organs, they're pretty important for what they do. Of course, the heart is going to be pumping throughout our lives because we need it. So it needs a very consistent and comprehensive circulation. So it will also have arteries and veins. Okay? So as it says here, it receives 5% of our systemic blood. So that's a lot because of what it does. Okay? And there are coronary veins because we're going to have kind of the same circulation, right? So we're going to need to have oxygenated blood, the gas exchange, and the internal respiration needs to happen, and then it has to go and get oxygenated again in the blood, in the lungs, right? Anastomosis is just branchings that are allowed to continue to receive, and it's just like little branching like this, and connections, okay? And this is just an adaptation of the heart, so if, God forbid, one of those main arteries or vessels gets blocked, blood can be diverted to other areas, right? Because if the main blood supply is only done by one artery, we're going to be in huge troubles, right? And that's why those anastomosis are very important. All right, so we talked a little bit about this, guys. So we talked about the left coronary artery and the right coronary artery. They're going to be on top of those sulci, okay? So think about where you guys are going to see it, okay? The right coronary artery it divides as the branching of the branching of the branching to the marginal artery and the posterior interventricular artery, okay? Then the left coronary artery is going to branch itself into the anterior interventricular artery and the circumflex artery, okay? We see it here. So we have the right and the left, okay? So let's follow it. So let's start with the right. So we have our right coronary artery that's going to be in that sulcus. We're talking about this boy here. But it's going to branch itself into the right marginal artery. But also it's going to branch itself in, this is, the reason this one is shaded is because it's in the back, right? So it's a right posterior interventricular artery that is going to be on top of the posterior sulci that is dividing those two ventricles, right? Now let's do it on the left side. We have the left coronary artery, and then we have the circumflex artery, but also it's going to divide to the anterior interventricular artery, okay? If there are arteries, they need to be veins. The veins are going to be stemming from the coronary sinus, and this one is posterior, and then you're going to have the great cardiac vein, the middle cardiac vein, and the small cardiac vein. So you think you kind of hug them, like if you're holding the heart with your hands, kind of like that's how it's being engulfed by both arteries and veins. You see them here. So we have the right coronary here that is going to turn into the marginal branch, and then it's going to also be branching into the posterior interventricular branch. From the left side, it's going to be the circumflex branch and the anterior interventricular artery, right? With veins, kind of the same. So we have the coronary sinus. We have the great cardiac vein. We have the small cardiac vein and the middle cardiac vein. All right. So I was telling you guys about the sounds previously. So the first lub, so meaning the tu, is going to be done by the closing of the atrioventricular valves. The second dub is going to be done by the closing of the semilunar valves. Okay? So what you hear when you're doing auscultation, meaning the listening of the heart sounds, is being caused by those closings. So of course I have to have first the lub, meaning the blood going through from the atrium to the ventricle, and then having those valves closed. Then when the ventricles squish, the blood is going to go to each respective aortic and pulmonary vessels, and then the closing of those valves is going to do the other sound. Sometimes, as I was telling you guys, some structures are going to be open and not working as they should be, and there is a third sound known as the murmur, and sometimes it's going to be like, it's just like, could be very sudden, could be very recognizable, and that's called a murmur. And it's just like a faint, it's just like a blow, like sometimes like that, or sometimes it can be very loud depending on what's going on with the heart. Sometimes they're innocent, sometimes they're not. It all depends what is causing that third heart sound. In children, it's very common, that's what I told you guys. 25% of humans walk around there with that fossa ovalis being like partially closed, and the flow of blood is causing that. Sometimes that can be dangerous because that can cause a clot, but some people just don't feel anything. If it's not messing with you, it's fine. Okay, here this is of course the image of a chest. The blue pieces is where the valves are located, okay? The yellow pieces is where you will hear them with your stethoscope, okay? So you will hear the aortic valve on the right side. Then on the left side, just off the sternum, you're gonna hear the pulmonary semilunar valve, the left one. Just by and below the sternum, you guys are going to hear the atrioventricular valve. And in this piece, in between, let's see, 1, 2, 3, 4, and 5 costal spaces. So this one is the, let's see, 1, 2, 3, 4, 5. So the fifth intercostal space is where you're going to hear this guy, okay? So why intercostal? Because ribs, that's the Greek term, costal for ribs, and the space in between the ribs is intercostal, and you guys are gonna be very familiar with them. So they start here, 1, 2, 3, 4, 5. Okay, so this is the fifth intercostal space. And now let's do it on the other side. 1, 2, second intercostal space on the right side, the second on the left side, and then this one here is just gonna be right below the sternum. All right, so this one, I suggest you guys take a break before you take a look into this. Why? Because this is when it gets a little bit complicated and where people get confused. Okay, so you guys have heard of a pacemaker, right? What a pacemaker does is when someone's natural pacemaker stops working, what the pacemaker does is it's stimulating the pumping and the activity of the heart. The heart itself has its intrinsic, meaning inside system that helps the heart to contract and beat. And this is important because it means that we don't need to do anything consciously to have our hearts being pumped and working, right? So this is called the intrinsic intervention of the heart. You also will be hearing the pacemaker or conduction of the heart, okay? So let's start. So this means that this intrinsic innervation has the ability to self-excite, meaning stimulate without involvement of any other body systems. There's influence of other body systems in the heart, but it doesn't need to be there to act, right? So the first piece of this is located in the right atrium, and it's called the sinoatrial node. You also will be hearing it as the SA node, okay? Sinoatrial means in the atrium, okay? It's located posterior, up and posterior of the wall of the atrium, and it's very close to the superior vena cava, meaning from above. Sometimes when people are getting catheters, some people try to tickle a little bit that SA node, then you might get a little bit of tachycardia, but just for a second, okay? So when the SA, meaning the sinoatrial node, is activated, both of the right and the left atrium contract. And this is a good time to talk about what systole means and what diastole mean. Diastole, you don't see it here, but think about systole as contraction, diastole as relaxation, okay? Going back to the pacemaker piece, as it says here, the sinoatrial node is known as the natural pacemaker of the heart, okay? And it has a beat rate. Initiates at 70 to 80. The other pieces of the conduction system of the heart have a rate as well. The things that you need to remember is this guy has the highest rate, okay? This system is as effective if this guy fails, the other pieces take over, but they're not as efficient as this one is, okay? You guys will see that the system starts from superiorly and it works its way to the rest of the heart. And this will make sense in a second. This piece, I suggest you guys take a break before we continue to this, because this is kind of complicated, okay? We are leaving a little bit of the anatomy part and going to more into the physiology piece of it. Okay, so from the sinoatrial node and the contraction, the impulse is going to move to another piece called the atrioventricular node, which is located inferior to the interatrial septum. Okay, so if the first guy was the SA node, was located kind of like superior and right of the atrium. This guy is like closer to the wall that divides both atrium, right? So it's going to be here, and of course it's going to be connected this way. And this branches go to the left atrium. This piece goes to the AV node, okay? Let me just erase this. Okay, so as I was telling you guys before, the one that has the highest rate is the sinoatrial, going from 70 to 80. This guy goes to 40 to 50 beats per minute, okay? So we have the SA node, meaning the sinoatrial node, and then we have the atrioventricular node, okay? Then from the atrioventricular node, it's going to move to another structure called the AV bundle, meaning the AV bundle or bundle of His, okay? Once we see the structure, it make a little bit more of sense, but just think about a sequence. So we started at the SA node, branching to the left atrium because both atrium need to contract. Then it's going to go to a atrioventricular node, and now it's going to an AV bundle, or known as the bundle of His, okay? Just kind of like a circuit, right? From there, it's going to split in two. And these are called the right and the left bundle branches, okay? This piece, meaning the bundle of His or the AV bundle, is in the interventricular septum, okay? All right, and then it's a little bit of branching of the branching is from the AV bundle, it branches out into a left and a right bundle, right? Then they're gonna branch out more, and these are going to be known as the Purkinje fibers, okay? And this is where the ventricles contract, creating the ventricular systole, meaning the contraction of the ventricles, okay? All right. So, as I was telling you guys before, we have contraction known as systole, and then we have a relaxation called diastole, okay? One happens after the other, never at the same time, because it will not happen. And always remember this: the atrium or the atria contract first, then the ventricles, okay? Because think about it like a little chamber pump. These guys need to squeeze first, so the blood goes here, and then these guys will squeeze here so it can go to the rest where it needs to go. If these guys will squeeze at the same time, there will be no blood being pumped or getting in, because it's like if you like squeeze a bottle, nothing's coming in or coming out, right? All right, so before we move to what an EKG means, we have to address a term that you guys have seen before. It is called the action potential, but also depolarization and repolarization. So going to anatomy 101, but also your chemistry. So we have an action potential, which means this is the threshold that needs to be met in order for a reaction to happen. Okay? So thinking about the cell wall, we know that there is more sodium outside and there's more potassium inside, right? So in order to have the action potential, some electrical activity has to happen. So the enough amount of stimulus, meaning enough to reach the potential action, is going to happen. So the ion exchange happens. So what's going to happen is with the depolarization, sodium is going to go inside the wall, and potassium is going to go out at some point. Okay? So let's track back a little bit. So the stimulus happens and it's high enough to reach an action potential, and it will be dependent of the amount of sodium going inside the cells. The action potential happens, and then when the happens and the depolarization happens, we need to go back to a resting state, right? And this is when the repolarization happens, and this is when potassium is going to go out of the intracellular space enough that it's going back to a resting state. And there's a point where the hyperpolarization happens, but it's going to be until things get equaled out, and then we go back to a resting state. All right? And this is the part that we kind of get like all worked out or worked up, because it's a lot of like abstract thinking. But just think about like the simplest terms. So there has to be a stimuli, right, in order for something to happen. So we're stemming from a negative resting stage, and then the stimuli is going to be high enough so the depolarization happens. So enough ions of sodium are going to go inside the cell that it gets depolarized, meaning that the charge inside and outside the cells switch. Okay? The stimuli and the purpose happens, but we cannot stay that way forever, so we need to repolarize, meaning that the balance is going to happen again. And in order to go that, potassium ions are going to go out to the point that the charge happens to a resting state and be negative. Okay? And this is called repolarization. Okay? And this is when potassium ions are going out, so the charge happens and everything goes back to a resting state. Okay? And this is going to happen simultaneously as needed, so the activity that we want to have, meaning maybe muscle contraction in this case, happens. Okay? So just look at the graph for a little bit and make sure you guys understand them, because we are going to talk about EKGs, and these terms of depolarization and repolarization are going to be thrown around, and I don't want you guys to be like, what are we talking about? Okay? All right, so now let's talk about a few things here. Well, let's break things down a little bit. First, of course, we see a heart here, but also here. I'm pretty sure you guys have seen this, not even on a medical presentation. You guys are very familiar here. You will see this in movies and places, and this is basically what's called an EKG, and this is called a PQRST cycle. Okay, this is what you guys would see in an EKG. And this is basically the graphic representation of the electrical activity of the heart. Okay? This one is like your picture perfect drawing of what an EKG should look like. I'll be honest with you, most of the time it looks like this, but when we are dealing with older populations, it would not look like this. And if someone has something like an underlying condition, it would not look like this. It will have some tweaks, but what you guys need to address is knowing the parts, measuring it, and what each thing represents. Again, this guy, it's the electrical representation of the heart activity. It does not represent contraction. It represents the electrical activity, okay? On the right side here, we have a heart. But if you guys see here, there are like some structures that we have not seen before. And these are the pieces that we were talking about, the intrinsic electrical circuit of the heart. And we are going to talk in detail about this guys first before we move forward. So first here, it's the one that we were talking first. This one is the natural pacemaker of the heart. This one is the SA node, the sinoatrial node. This is the guy where the conduction starts, and this is going to be like the chief where the electrical activity happens. Okay, so the stimuli and the electrical stimuli is going to stem from here, and it's going to radiate to the left atrium, and then from here is going to go to the atrioventricular node, or the AV node. Okay, and if you guys see here, they're still on the atrium, but this SA node is here close to the vena cava, superior vena cava, and then this guy here, the AV node, is close to the septum. Okay, so again, we start from the SA node, or the sinoatrial node. The electrical stimuli is going to stem and go to the left atrium, but firstly and mostly it's going to also go to the AV node. Okay, from the AV node is going to go to the bundle of His. Okay, in the bundle of His is going to stem to the bundle branches, the left and the right one, and from there it's going to stem to the Purkinje fibers. Okay, this complex or system, it's going to be responsible for the electrical conduction of the heart. Okay, so we start by the SA node, then go to the AV node, then the bundle of His, then the bundle branches, and then the Purkinje fibers. Okay, and if you guys see here, those Purkinje fibers are going to be located in the heart muscle. The branches and the bundle of His are going to be in the septum, AV node by the interatrium septum, and then the SA node is going to be close to the vena cava, the superior one. Okay, having that said, we know again the order of events. First the SA node, first the SA node, then the AV node, then the bundle of His, then the branches, and finally the Purkinje fibers. Okay, and this is what is going to dictate the electrical activity and then the contraction and relaxation of the heart. Okay, we talked about what depolarization means and what repolarization means. Okay, so first piece, going back to the EKG. Okay, we have a P wave, our QRX complex, and a T wave. This is a representation of electrical activity. Okay, these guys can be measured, these guys can be timed, and these guys are going to indicate how the conduction and communication between the different parts of the intrinsic conduction of the heart are working. Okay, so this should be the representation of a normal EKG. Okay, so let's start with the atrial depolarization has started in the SA node. Okay, this depolarization meaning that we have reached enough stimuli to cause the ions of sodium to go into the intracellular space, changing the charge on those muscle cells, so that depolarization is happening. Okay, and this is represented by the P wave. Okay, then when that depolarization is complete, the impulse is delayed at the AV node. That impulse is delayed at the AV node, and that is why this piece is showed here. Okay, then there's a depolarization that begins at the apex, causing the QRS complex. Okay, at this moment the atrial repolarization occurs. So now we're going to go back to here, and this is where the repolarization occurs, meaning potassium ions are going out enough to change the charge of that cell wall to negative, and everything goes back to our resting state. This is why I wanted to show what depolarization and repolarization mean, and why the EKG looks like that. Okay, again, this is the representation of electrical activity. Okay, so we start by the P wave when the atrial node is being depolarized. Then that stimuli is delayed at the AV node. Once the depolarization is complete at the SA node, and then the ventricular depolarization is happening at the ventricular level, being represented by the QRX complex. And at that point, the repolarization happens at this level. Okay? Subsequently, we already talked about things getting depolarized here, being completed here, and then the ventricular depolarization happening at this complex. Being complete gets to this point, but then if depolarizes, it has to repolarize, right? Because it cannot stay at some point forever. That is being represented by the T wave. Okay? When the repolarization is complete, we go back to resting state. Okay? Think about this as positive and this as negative. So we are becoming more positive, complete, going to a resting state, and then getting positive because we are depolarizing, getting that complete, repolarizing, going to resting state. Okay? Again, this is the representation of electrical activity of the heart, not contraction. The contraction is going to happen at some point, but first we have to have the electrical stimuli for those muscle cells to contract. Okay, so here we got it. This is the conduction of the heart. Everything starts as a sinoatrial node. That stimuli is going to spread to the left atrium as well, and of course to the right atrium. Then it's going to jump to the atrioventricular node, also known as the AV node. Then it's going to jump to the atrioventricular bundle or bundle of His, and then it's going to spread to the right and left branches, and subsequently to the Purkinje fibers. The Purkinje fibers are located in the muscle walls of the ventricles. The atrioventricular node or bundle is going to be located in the septum, okay? And so are the branches, okay? So the stimuli starts here. This is the bus. If this guy fails, the AV node is going to take over. But it's not as efficient, but it can take over. And our heart rate can be conducted, but it's not going to be as efficient. If this guy fails, this guy can take over. And of course, at this point, this guy can take over, but it's very, very inefficient pumping, and the heart rate is just miserable. So they just try to do their best, but not as efficient, okay? So first, SA node, second, AV node, third, AV bundle or bundle of His, then the branches, and then the Purkinje fibers, okay? This is called intrinsic conduction of the heart, okay? Here we have her again. So intrinsic innervation of the heart or conduction system pathway. So we started the SA node, then the AV node, then the bundle of His, then the branches, and then the Purkinje fibers. All right, so we got the EKG, also known as the electrocardiogram, also known as the ECG, or also known as a 12 lead. It also can be an 8 lead, so you'll see more often than not that people will use that as an EKG, okay? So as I said before, this is the recording of the speed of electrical impulses across the wall of the heart, okay? Again, it's electrical representation, not physical activity, okay? And that's what I wanted to touch base about the action potentials, what depolarization and repolarization mean. And now let's talk about how the EKG is done. So it will be placed on using electrodes on the chest, arms, and legs. And this is when it's done with a 12 lead EKG, okay? And as it says here, sometimes it's just the chest when they only use an 8 leads EKG. So what it does is like the machine measures the data and prints out the record. And you guys have seen this at some point. It's just like, it's like a pinkish paper, and then you guys will see the recording on that, okay? And a typical EKG has what we have talked before, has a P wave, has a QRS complex, and then a T wave. And we're gonna talk in detail about that, okay? So here you will see which a normal EKG looks like. Nice, even, and gorgeous, okay? So it has a P wave, then it has the QRS complex, and then we have a T wave. And what happened is like the next one will be similar to this one. It just goes on and on and on, okay? Because a heart has to be beating at an even and constant rate. If we have pauses or if we have something going on, it's when we see like the abnormal pieces, okay? So again, the P wave is the depolarization of the atrium SA node. Then when the depolarization is complete, it's being relayed to the AV node. Then the ventricular cell walls are being depolarized. When the depolarization is complete, then it's getting repolarized. And then the cycle is done, okay? For what pertains to me, and what you guys need to know, is knowing how to point where the P wave is, what the QRS complex is, and what the T wave is, and what it represents, okay? Okay, so the P wave represents the atrial depolarization, okay? This contraction piece here It's kind of misleading, but you guys will see the contraction at some point. But as you guys notice here, first is the electrical activity, and then is the physical activity. But it's not represented here, but it will match at some point when that happens, okay? Then the QRX complex is the representation of the depolarization of the ventricular wall, and this is where it happens, okay? And then the T wave represents the ventricular relaxation, okay? So now we're seeing the electrical stimulation that is going to cause the contraction, and that contraction is going to be pumping of the blood, okay? So depolarization causes contraction, meaning systole. Repolarization causes diastole, relaxation. So we are looking at something stimulating the heart to contract and then goes to the baseline to relax, okay? This cycle is going to help our heart to do what it's supposed to do, pump blood, okay, in a way that is efficient, constant, and is lifelong until we die. All right, going back to our little diagram, we know where the different nodes and branches are, so we're gonna go back again. So the atrial depolarization happens, stimulating atrial contraction, right? Then the depolarization is complete, and then the depolarization of the ventricle walls happen, helping to create the next contraction. As you guys notice, these guys don't contract at the same time because it's not efficient, because otherwise there's not going to be enough time for fill and eject blood, okay? So once the depolarization happens, it's complete, it goes to this baseline, and then you guys see the depolarization happening here in the ventricle walls. Now on the next slide, we're going to see that this depolarization is complete at this point, okay? And as you guys see here, the depolarization is complete, and then being depolarized has to repolarize, right? Why? Because it cannot stay at one point, because something cannot be perpetually contract, okay? Especially the heart muscles, you don't want that. So the repolarization happens here of the ventricles, okay? Beginning at the apex. And then the repolarization is complete. The next piece that you guys will see is just another cycle, okay? There you go. So at this point, this is another good time to take a break, because the next pieces are going to be a little bit complicated, and you guys need to understand this, okay? So each cardiac cycle takes 0.8 seconds, okay? And basically describe volumes and pressures of each chamber changing from contraction to relaxation, okay? So we have 4 phases: ventricular filling, isovolumetric contraction, ventricular ejection, and isovolumetric relaxation. Here, this is kind of a little bit confusing. It's gonna make you confused. Look at this guy here. As I was telling, this is the whole cardiac cycle. And there's a little pause. It's itty bitty, it's not big. But if you guys see next, there's another cycle starting, okay? Here, what you guys are seeing, it's pressure. And it's being created by blood going to each chamber, being pushed against valves, and then being ejected from there, okay? These are the hard sounds we have talked about when the valves close and when there's the lub and the dub, okay? Then the volumes, this is in mLs, and this is going to happen when contraction and relaxation happens, okay? And this is each phase of the cardiac cycle, okay? So we have an atrial systole, meaning an atrial contraction. Then a ventricular systole, meaning a ventricular contraction. and then a relaxation period. Okay? Let's start with the simplest. Let's erase these guys for a second, okay? So that way it doesn't get too overwhelming. Okay. First, we got a depolarization of the SA node. And as I told you guys, this is electrical representation. The contraction is going to come later, okay? So the stimuli is there and it's telling electrically to the cardiac muscles of the atrium to contract. And that's why you guys are seeing down here. Let's just erase this, and I'm not using the eraser. There you go. Okay. So these two chambers over here are going to contract, okay? That contraction is going to push blood to the ventricles, right? Because it comes from the atria to the ventricles. So atrial systole, meaning atrial contraction. So the bicuspid valve closes here. And it's also the beginning of the first heart sound, okay? Since we are talking about contraction, the diastolic volume, and we're going to talk into detail there, ends, okay? Now, there is depolarization of the ventricles, meaning that the next action is going to be that the ventricles are going to contract. See how delays this? Because the electrical activity is here, but the action itself is happening here. So the aortic valves open because there's going to be contraction, and that force is going to open these valves, okay? The stroke volume is the amount of blood that is being ejected from the from the ventricle, and this is what is being represented here, okay? This is where the ventricular ejection happens because they're being squeezed. And as you guys notice, I have skipped this guy because this guy is not pleasant here, but basically is the point, and this is a very, very tiny point where there's isovolumetric contraction, where there's no contraction itself. It's just like everything is being contained before it starts to push and contract, okay? Then the depolarization is complete and it needs to repolarize, meaning that those ventricles are going to relax, right? So the blood was ejected. There's a isovolumetric relaxation. But as you guys can see, since the blood being ejected is complete, some blood might start to like track back, and this is where those kind of swallow nest shaped valves work, because if the blood is trying to come back, it's gonna fill up these valves, closing that valve, okay? And the closing of these valves are going to cause the second sound, lub dub, okay? Then at this point, we're going to have some ventricular filling, and this is just like the passive flow of blood from the atria to the ventricles, and this is just a little amount of volume, and this is usually known as a third sound that is not physiologically speaking. When you auscultate yours, it's not like you guys are going to hear it, okay? And then we start the cycle again with atrial contraction, okay? This diagram can be very overwhelming, but if you break it down and just like we just did, makes a little bit more sense, okay? And this piece with the pressure, think about like what's opening, what's closing, and pressures, okay? I'm not gonna ask you for matters of exams to know the pressures, but it's important to know what's going on here, okay? Okay, so now let's start with the 4 phases of the cardiac cycle. The things I want you to remember from this are the following, okay? We're going to talk about the ventricular filling. So the ventricles just ejected a bunch of blood, and the pressure in them is not as hard as when they just like contract, right? So what's going to happen is like some blood is going to passively flow from the atria to the ventricles because the pressure in the ventricles is not as hard or high, so those AV valves are going to open. And blood, think about it as just like the trickle. I think about the ventricular filling as the trickle, okay? The semilunar valves, meaning the valves that are like the swallow-shaped valves in both pulmonary trunk and aorta, are closed because the pressure in the ventricles is not great enough, but also there's blood trying to backflow, and that's why those valves are closed, okay? Now, keep in mind where we are at with this. This is the beginning. This is like the middle of the hump of the first wave, okay? All right, so the volume of the blood present in the ventricles at the end of ventricular filling is known as end of diastolic volume, okay? Keep that in mind. The volumes, meaning the amount of blood present in the ventricles at the end of the ventricular filling is known as end of diastolic volume, okay? The pressure in the ventricles is now higher because it's filling up, and it's going to cause the AV valves to snap shut, causing what? The first sound of the lub, okay? That's what happened. So blood is trickling first passively from the atria to the ventricles because the pressure in the ventricles is low enough that the AV valves opened, right? As they filled up, it's going to cause the pressure of the ventricles to increase because we're filling up, right? However, the pressure is not high enough for those semilunar valves to be open. But we're getting there. At the end of that ventricular filling, the amount of blood that is going to be there is going to be called end of diastolic volume, right? The pressure increases high enough that those AV valves that initially were open are going to snap shut, and that snapping shut is going to cause the first hard sound, okay? Okay, so now let's talk about the isovolumetric contraction. This is a very short-lived period of time, and this is at the same time where the QRX complex is present or happening, and is when the ventricles are depolarizing, okay? At this moment, the ventricles are beginning to contract, so think about, so we have atria here, and we have ventricles here, right? So the ventricles are getting started to contract, not fully there yet. And all 4 valves are closed, okay? And this moment is where the pressure is starting to build up. All right? So the contraction is just starting, and the pressure is mounting up. But all 4 valves, meaning the AV valves and both semilunar valves, are closed, okay? On the ventricular ejection piece, the contraction continues to happen, pressure is building up, so exceeds the blood pressure of our bodies, and this pushing of blood, it's going to push the semilunar valves to open, and blood is going to go through, be ejected from the ventricles. Okay? The volume of blood ejected from the ventricles in one heart contraction, meaning think about it in one squeeze, is going to be called stroke volume. Okay? The amount of blood that remains after this contraction or ejection of blood is known as the end systolic volume. So think about, we squeezed that bottle, and whatever is left in that bottle is called end systolic volume. Okay? So to repeat, in the ventricular ejection phase, the ventricles are still contracting to the point that the pressure is building up enough that the pressure is going to open those semilunar valves. The blood is going to be ejected, and that amount of blood that is going to be ejected in that, sorry guys, I was choking a little bit. So in that contraction, the amount of blood that is going out of the ventricles in that contraction is called stroke volume. The resting amount of blood left in those ventricles is known as end systolic volume. Okay? Kind of similar to the isovolumetric contraction, this is isovolumetric relaxation. So this is when the pressure of both ventricles become less than the body's own pressure. The blood in the aorta and the pulmonary trunk start to backflow, meaning that the blood is going to try to return. And this is where the semilunar valves are going to close, because as we were mentioned, they kind of have like a little ball or like cup shape. So the blood is going to try to back up, they're going to fill up, and they're going to shut. This is what causes the second heart sound, the dub. Alright? And at this point, not only the semilunar valves are closed, but also all the other 4 valves are closed. Okay? The ventricles are relaxing, and they are preparing for the cycle to start again. Okay? And all this cycle, it only takes 0.8 seconds. Okay? Alright, so heart rate. Heart rate is the number of beats that occur in 1 minute. Okay? This is what you guys will feel when you measure someone's pulse. Alright? Usually in adults, you will feel it around the radial pulse, meaning like around the wrist, on your thumb, or below your thumb on your wrist. Okay? Heart rate will be the amount of beats during the length of a cardiac cycle. The cardiac cycle is the one that we talked about, 60 per minute. Okay? Alright, so now we're going to talk about cardiac output and stroke volume. We already talked about stroke volume, so this is the volume of blood that's going to be ejected in the contraction of the ventricles. Okay? So thinking about, I squeezed the bottle, and the amount of blood that I squeezed is the stroke volume. Okay? Basically, what it's saying here is stroke volume equals the end of diastolic volume minus the end systolic volume. Meaning, we know there's amount that was left when the blood was filling in the ventricles, and there's an amount of blood that is left after the ejection. The difference between these two will make the stroke volume. What you guys need to remember is what the stroke volume means, meaning the amount of blood that is being ejected from the ventricles when they contract. Okay? Just like a amount of blood ejected in one contraction. Okay? Now, cardiac output is the volume of blood ejected from a ventricle per minute. Okay? So, mathematically speaking, I know that the cardiac output is the heart rate, meaning the beats per minute, times the amount of blood coming from each contraction. Okay? All right, we are done with the complicated part. I highly recommend to review and look for videos online about those different volumes, as well as the cardiac cycle and what each of those pieces mean. Okay? Now we're done with that. Now let's talk about the extrinsic innervation of the heart. So we talked about, you guys remember, with the SA node, the AV node, and all that kind of jazz. That was the intrinsic intervention of the heart. This one is the extrinsic, meaning the out variables and factors around the heart or outside the heart that influence and regulate how the heart works. Okay? So this is an extrinsic innervation of the heart, and there are two main areas. There is a cardio-acceleratory center and a cardio-inhibitory center. So just from looking at these two terms, we kind of deduce what they do, right? This one promotes and increases the functioning of the heart, and this one decreases the functioning and performing of the heart. All right? So, first one, cardio-acceleratory center, located in the medulla oblongata. If you guys remember this area, it's also where some of our respiratory control is, okay? So this one sends impulses through the sympathetic nerve fibers to the cardiac fibers, cardiac nerves. And if you guys remember, the sympathetic system, it's always a increase, let's call it, response. This is part of your flight or fight response. So it's going to increase our heart rate, right? It uses a neurotransmitter known as norepinephrine, and you guys are familiar with another name for this guy known as adrenaline, right? And if you guys think of adrenaline as something that excites us and makes us perkier and makes us more active, that's the purpose, because it makes us ready to fight or flight, okay? On the other hand, cardio-inhibitory center, also located in the medulla oblongata, will do the opposite. So the parasympathetic means that it's going to make us rest and decrease our heart rate, because maybe we need this to relax. We don't need that much stimuli, and it's using the vagus nerve to do this. If you guys think about the vagus nerve, I have told you about like the Valsalva maneuver. It's when we bear down, what we are creating is a vagal response, decreasing the heart rate. The neurotransmitter that is used is the acetylcholine, and this one decreases the heart rate. Okay, this should be very explanatory. So the acceleratory increases and the inhibitory decreases. Okay, so this is a little diagram. So we have here our spinal cord, and if you guys think about, we have a posterior area that is going to be inhibitory, and I'm going to erase that. There you go. It's going to be inhibitory, and then in this area of our nerves is going to be the sympathetic, which means increases. So if you guys follow the green line, you guys are going to see that it's going to the same areas where the intrinsic conducting piece of the heart is acting. Meaning if the sympathetic nerves are meant to increase or accelerate the heart function, it's going to increase aid by the adrenaline piece. In the other side, we want to decrease, and this blue nerves are going to do the opposite thing, decreasing the heart rate, aid by acetylcholine. Okay? So acceleratory increases, inhibitory decreases, right? So parasympathetic decreases, sympathetic increases. Okay? Abnormal heart rates. This is very straightforward, guys. Brady, it also always will mean slow cardia regards to the heart. So if it's below the normal heart rate, it will be bradycardia, right? If it's above, it will be tachycardia. If it's at tachy, it's fast. Brady, slow. Bradycardia, slow heart rate. Tachycardia, super fast heart rate. Of course, we don't want either this one or this one. We want our normal heart rate. Okay? That's it. Thank you so much, guys.